Hello, this is Mr. Drach. Today we're going to be talking about classifications and properties of matter, ways to describe things like the ice cube you see on the right side of your screen. We're going to be talking about what it feels like, how heavy it is, the state it's in, like a solid, and things of that nature. So we're going to start off with properties of matter, and in this case we're going to start off with physical properties. Physical properties are any sort of properties that you can observe without changing the substance composition. That means what it's made of. For example, if you notice in the bottom right, we see some gold, and we can tell a few things about the gold without changing what's in the gold. So whatever we notice, it's still going to be gold after we notice it. A few examples of physical properties when talking about that gold would be things like the color of the gold. We can tell that without changing what's in it. We could tell things like the mass. We could weigh it and it's still going to be gold. We could tell the volume of it. And with those two, we could figure out density of the gold. So all of these are physical properties. And so telling something about it without changing what it really is. Now that's different from a chemical property. A chemical property is a property of matter that you can observe only by changing its composition. For example, over on the right, we have an iron nail. So over here, this is iron nail. That's the symbol for iron. And a few things we can tell about that where we would have to change it would be things like how flammable it is. If we burned it, we would be changing what's inside of it. We'd be changing its composition, what it's made of. A few other things that we could tell about it is something like how it reacts with an acid or its reactivity. Or we could even say how it's going to rust too. Okay, in any of those cases, we would be changing what's in it. For example, if it rusts, we're changing it from iron to iron oxide, which that would be iron oxide, iron 3 oxide anyway. Okay, so those are chemical properties. Now, we're also going to be talking about physical and chemical changes. And these are changes that happen to things where we're either going to change the composition or not. And the big thing to differentiate between the two is whether it's reversible or not. And that means if we can change it back or not. So we're going to start off with physical changes. Physical changes are when some of the properties change but not the composition. And again, the composition is what it's made of. Usually this is reversible. We'll go over some examples on the next slide. And then we have some chemical changes, and that's when the composition changes, and usually it's not reversible. Usually we cannot change it back. Now, a few of these signs that a chemical change occurs, we're going to see next. So some signs of a chemical change. And we're going to be using the example of a fire. Okay. In a fire, if you notice the logs might start off as kind of a brown color, but they're going to change color in a chemical reaction. And let me back up for a second. Now, these changes may not occur in every reaction. So you may not always see a color change or a heat change, but most of the time you're going to see almost all of these, like in a fire. So we have a color change. The wood turns from brown to a black or gray color. Heat change. Obviously, if we burn something, it's going to change the heat given off. Irreversibility, and that means, again, if we can change it back or not. In a chemical reaction, we cannot change it back. And I'll just write that right down here. Cannot change back. Almost all the time. We also get some gas production. In this case, with the combustion of wood or fire, we're going to get some carbon monoxide, some carbon dioxide, some smoke, things like that. In fact, most people die from the gas production given off from a fire rather than the heat. And then lastly, a precipitate. We're going to talk about what that means in just a little bit, but for now we're going to focus on the color, heat, irreversibility, and gas production. Okay, so let's go through a few examples and see if we can tell if it's a chemical or a physical change. If I were you right now, I'd actually hit pause and see if you guys can figure out if it's a chemical or physical change. And we're going to write a C for a chemical and a P for a physical change. So go ahead and hit pause, see if you can classify those, and I'll give you a second while you pause your computer. Okay, I wonder how many of you actually pause your computer. Probably not that many. That's okay. Let's go through these. Okay, butter melting. Butter melting would be a physical change because we're not changing what's in it. Even melted butter is still butter, and we can change it back as well. We can change melted butter back into solid butter by putting it in the refrigerator, right? So we can change that back. Salt dissolving in water. This is again a physical change because I can change it back. I can get the salt back out of the water, and so on. Wood burn, this is a chemical change. I cannot unburn wood, so definitely chemical, and we kind of went over that last slide. Bread is toasted, again chemical. You cannot untoast bread, and in fact you're burning it a little bit. Breaking glass, that's physical because it's still glass. We could actually put it together and recycle it if we really wanted to. Water evaporating, again a physical change. We can get that back. Paper being ripped, it's still paper. Didn't change composition, physical change. Leaves changing color. Can you change those leaves back? No, they're dead. When they come back in spring, those are brand new leaves, not the same leaves. And metal rusting, that's again chemical. We can't change that back, and we're changing the composition. Okay, next we're going to talk about states of matter. The three main ones are solids, and we use a little S with parentheses around it. A liquid, again, parentheses, that's an L, and a gas. Those are the three states of matter. You can see how the particles are arranged. In a solid over here, you'll notice the particles are very close together. As we heat them up, they might melt and turn into a liquid. The particles are a little farther apart, moving around randomly. And then if we heat it up even more, it turns into a gas where the particles are all bouncing around and are much farther away from each other. So those are the three main states of matter, and you'll see those abbreviations when we're talking about different elements and compounds. Like our ice at the beginning, we would call that a solid and put a little S after that, solid water. Okay, another thing when we're talking about solids, liquids, and gases are the volume that they have. We say that some of these have a definite volume or shape, or no definite volume or shape, and we'll start off with solids. Solids do have a definite shape, and they do have a definite volume. And that means it doesn't matter the container we put them in. They'll still have the same shape and still have the same volume. Now liquids will change shape when we put them in a container, but they'll still stay the same volume. So we say they have a definite volume. And lastly, gases. Gases have neither a definite shape or nor a definite volume. And they'll take the shape and size of any container you put them in. So that's what we call the shape and volume of their solids, liquids, and gases. Okay, next we're going to move to the difference between elements, compounds, and mixtures. And we're going to start off with what are called the pure substances, the elements and compounds. Elements are made up of one type of atom, and you can see on our periodic table up here, those are all the different types of elements, and they're all are composed of one type of atom. Some examples would be like our iron or helium, etc. So those are all one type of atom. Now a compound has more than one type of atom in a fixed ratio. An example there would be like water. Water, we have 2 parts of hydrogen to 1 part of oxygen, so a 2-to-1 ratio. We could also have something like potassium sulfate. Here we have 3 types of atoms, and here we have a 2-to-1-to-4 ratio. So they all come in fixed ratios, and they're composed of more than one element. We can tell that because there's more than one capitalized letter in those formulas. Now, on to mixtures. Mixtures could be something where it's a bunch of elements and compounds all just kind of mixed together. And we have 2 different types of mixtures. We have homogeneous, some people say homogeneous mixtures, and those have uniform composition, meaning they look the same all the way throughout. We can't tell the little bits and pieces they're made of. Some examples would be like steel. Okay, steel is made up of a mixture of iron and carbon, sometimes some other ones like cobalt. But we can't really tell the different parts, right? And the opposite type of mixture is called a heterogeneous mixture. And this has no uniform composition. That means they don't look the same throughout. They look all different throughout. A good example here would be sand. If you look closely at sand, you can see some dark particles, some light particles. They're different sizes, and they all look different. So that would be a heterogeneous mixture. Okay. One special type of homogeneous or homogeneous mixture is called a solution, and we're going to see a lot of these this year. This is when a substance is dissolved in another substance, usually dissolved in water, but it could be something else. A good example is kind of like my picture over to the right, and this would be sugar water. Okay. In this solution, our sugar is dissolved in the water, and notice over here it has a uniform composition. It looks the same throughout. We can't really tell the sugar from the water or anything else. Now, the symbol here for a solution is AQ. AQ stands for the word aqueous, and that means it's in water. Aqua would be water, aqueous, aqua, so on. Okay, so that's a special type of homogeneous mixture. Okay, now I kind of wanted to get to the fifth sign that a chemical change is occurring, and that's a precipitate. When we have an aqueous solution, like A, and let's call this stuff A, and we have another aqueous solution, B, sometimes when we mix them together, we get a solid, and that would be C, and that would be this yellow stuff right down here. That would be our solid, and that is our precipitate. Okay, and that would be another sign that a chemical reaction is occurring with solutions. Okay, next to last, just a kind of a graphic organizer for all matter. We've got our elements, mixtures, and our two types of compounds. We're going to practice on classifying these. Okay, so first thing you want to ask yourself is, can it be separated physically? If yes, then it's going to be a mixture, and if no, it's going to be a pure substance, which is an element or a compound. Now, an element would be something like hydrogen or oxygen, and if we put those two together, we would get a compound. And only chemically can they be separated to get to the elements. Then we also have our homogeneous or homogeneous mixtures, like a solution. Okay, and they look the same throughout. A good example here would be like Kool-Aid. Or a heterogeneous mixture, something maybe like dirt, where all dirt particles don't look the same, they look all different kind of throughout. So we've got our mixtures and our pure substances, elements, and compounds. So let's try a few and see how we do about classifying a few different things. Again, if you'd like to hit pause and try to do this on your own, we're going to classify these as elements, compounds, homogeneous or homogeneous, or heterogeneous mixtures. And we'll see what they are. So if you want to hit pause now, go ahead. See how many hit pause this time. Okay, we're back. Let's go see and how we do. Salt is going to be a compound. The symbol for that is, I kind of wrote that badly. Hang on one second. Let's try erasing that. The symbol would be NaCl. Okay, so two different elements, two different capitalized things. So it's going to be a compound, two elements chemically combined. Pepper. Pepper, not all of the pepper particles look the same, so that would be a heterogeneous mixture. Aluminum. Aluminum's on the periodic table. It's made up of one type of atom. That's an element. Gravel. Gravel is another heterogeneous mixture because it does not look the same throughout. Salt water. That's another type of solution, and it looks the same throughout. That is going to be our homogeneous or homogeneous mixture. Wood. If you look at wood, it has different colored particles, so that's going to be heterogeneous. Air. Air is one that a lot of people get kind of confused, but if you think about it, there's carbon dioxide, there's nitrogen, there's oxygen, and a bunch of other gases floating around, and they're all mixed together. It's a mixture, and that would be a homogeneous or homogeneous mixture unless you live in Los Angeles, where it's very smoggy, and you can definitely tell the difference between particles of air. Hydrogen, this would be an element. It's on the periodic table. And carbon dioxide, CO2, that is going to be a compound because two different elements, carbon and oxygen. Anyway, that does it for the classification of matter and properties thereof. Hopefully you learned a little something today. I will see you later. This is Mr. Drach saying goodbye.